This is the video for section 4.2, divisibility in f bracket x. Now that we have a division algorithm for polynomials over a field, we can introduce the ideas of divisibility and the greatest common divisor in polynomial rings. As we'll see, many of the results that hold in the integers also hold in f bracket x, where f is a field. We assume throughout this section that f denotes a field. We'll start with our definition. Let f be a field, and let a of x, b of x be polynomials in f bracket x with b of x not equal to 0. Then b of x divides a of x, or b of x is a factor of a of x, which is denoted b of x with a vertical bar and then a of x, provided that there exists h of x in f bracket x such that a of x is equal to b of x times h of x. For an example, in q bracket x, we can show that the polynomial 3x minus 4 divides 6x squared minus 5x minus 4, and the polynomial 2 times 3x minus 4 also divides 6x squared minus 5x minus 4. Since 6x squared minus 5x minus 4 can be factored as 3x minus 4 times 2x plus 1, then 3x minus 4 divides 6x squared minus 5x minus 4. Now in this factorization, we can put a 2 in front of the 3x minus 4 and a 1/2 in front of the 2x plus 1 to compensate. And this shows that 2 times 3x minus 4 also divides 6x squared minus 5x minus 4. So as in this example, we can show in general that whenever a polynomial b of x divides a polynomial a of x, any non-zero constant multiple of b of x will also divide a of x. This is part of Theorem 4.7. Suppose f is a field for all a of x, b of x in f bracket x with b of x non-zero. If b of x divides a of x, then c times b of x divides a of x for each non-zero c in the field f. And 2, if b of x divides a of x, then the degree of b of x is less than or equal to the degree of a of x. To prove this, suppose a of x, b of x in f bracket x are arbitrary polynomials. To prove 1, suppose b of x divides a of x. We need to show c times b of x divides a of x for each non-zero element c in f. So suppose c in f is an arbitrary non-zero element, we need to show c times b of x divides a of x. Since b of x divides a of x, then there exists an h of x in f bracket x such that a of x equals b of x times h of x. Since f is a field and c is not equal to 0, then it has a multiplicative inverse. Then a of x, which is equal to b of x times h of x, can be written as 1 times b of x times h of x, and 1 can be replaced by c times c inverse, and we can rearrange the factors to write this as c times b of x times c inverse times h of x. And this implies c times b of x divides a of x. And this proves part 1 of the theorem. For part 2, suppose b of x divides a of x again. We need to show the degree of b of x is less than or equal to the degree of a of x. Since b of x divides a of x, then there exists an h of x in f bracket x such that a of x equals b of x times h of x. By Theorem 4.5, the degree of a of x will be the sum of the degrees of the factors on the right, so this will be the degree of b of x plus the degree of h of x. Since degrees are non-negative, this implies the degree of a of x is greater than or equal to the degree of b of x. And this proves part 2 of the theorem. Next, we want to discuss the greatest common divisor. The GCD of two integers is the largest integer which divides both of them. We might expect the GCD of two polynomials to be the polynomial of largest degree which divides both of them. However, if d of x divides f of x and g of x, then any constant multiple of d of x will have the same degree and will also divide f of x and g of x. The GCD will then not be unique. In order to obtain a unique GCD, we require that the GCD be the polynomial with leading coefficient 1, which divides both f of x and g of x. In general, a polynomial with leading coefficient 1 is called monic. Now for any non-zero polynomial f of x, if c is the leading coefficient of f of x, then c inverse times f of x will be a monic polynomial. So by just multiplying any polynomial by the multiplicative inverse of its leading coefficient, we obtain a monic polynomial. Next, we have the formal definition of the greatest common divisor. So let f be a field and let a of x and b of x be polynomials in f bracket x not both 0. Then the greatest common divisor of a of x and b of x is the monic polynomial d of x of highest degree that divides both a of x and b of x. So thus d of x is the GCD of a of x and b of x, provided that d of x is monic, and first d of x divides a of x and d of x divides b of x, so d of x is a common divisor of a of x and b of x. And second, for all c of x in f bracket x, if c of x divides a of x and c of x divides b of x, then the degree of c of x is less than or equal to the degree of d of x. So this is saying that that d of x has degree greater than or equal to any other common divisor of a of x and b of x. For an example, let's find the GCD of f of x equals 6x squared minus 5x minus 4 and g of x equals 6x minus 8 in the polynomial ring Q bracket x. Now, as shown in the previous example, g of x divides f of x. So g of x is a common divisor of both polynomials. Since any common divisor of f of x and g of x must have degree less than or equal to the degree of g of x, which is 1, then the GCD must have degree 1. And since 1/6 times g of x equals x minus 4/3 is also a common divisor of both polynomials that is monic, then it must be a GCD of f of x and g of x. For another example, we can find the GCD of f of x equal x squared plus 1 times x cubed plus x squared and g of x equal x cubed times x plus 1 squared in the polynomial ring Z2 bracket x. Well, first note in Z2 bracket x, f of x, which is x squared plus 1 times x cubed plus x squared, can be factored as x plus 1 quantity squared times x squared times x plus 1. So x squared plus 1 in Z2 bracket x factors as x plus 1 quantity squared. And so this is equal to x squared times x plus 1 quantity cubed. Now the greatest common divisor is then obtained by combining the highest power of each distinct factor that appears in both f of x and g of x. So the common factors of f of x and g of x are x and x plus 1. And the highest power that appears in both f of x and g of x for x is x squared. The highest power of the other factor, x plus 1, that appears in both f of x and g of x is x plus 1 squared. So the greatest common divisor, d of x, will be x squared times x plus 1 quantity squared. Now with the above definitions, the results proved in Chapter 1 for divisibility and the greatest common divisor of integers have analogues for polynomials. We'll start with the analog of Theorem 1.2. So Theorem 1.2 stated, for all integers a, b, and d, a and b not both 0, if d is equal to the greatest common divisor of a and b, then there exists not necessarily unique integers u and v such that d is equal to au plus bv. Furthermore, d is the smallest positive integer that can be written in the form au plus bv. So this theorem shows that in the integers, the greatest common divisor of two integers a and b is the smallest positive integer that is a linear combination of a and b with coefficients in z. Our next theorem shows that in f bracket x, the greatest common divisor of two polynomials, a of x and b of x, is the smallest degree monic polynomial that is a linear combination of a of x and b of x with coefficients in f bracket x. So this is Theorem 4.8. Let f be a field for all a of x, b of x in f bracket x, not both 0, if d of x is the greatest common divisor of a of x and b of x, then there exists not necessarily unique polynomials u of x and v of x such that our GCD d of x is the linear combination a of x, u of x plus b of x times v of x. Furthermore, d of x is the smallest degree monic polynomial that can be written in this form and is unique. To prove the theorem, suppose a of x and b of x are arbitrary polynomials in f bracket x, a of x and b of x not both 0, and suppose d of x is the greatest common divisor of a of x and b of x. So we want to show that there exist polynomials u of x and v of x such that d of x is equal to a of x u of x plus b of x v of x. According to the second statement in the theorem, the greatest common divisor d of x will be the smallest degree monic polynomial that can be written in this form as a polynomial linear combination of a of x and b of x. Now we can model the proof after the proof of Theorem 1.2. In Theorem 1.2, we showed that the GCD of two integers a and b equals the smallest positive integer that can be written in the form au plus bv for some integers u and v. To prove this theorem, we let S be the set of all positive linear combinations of a and b. So S was the set of elements am plus bn, where m and n are integers, and am plus bn was strictly positive. We applied the well-ordering axiom to show that S had a smallest element, which we then showed was the greatest common divisor. To prove Theorem 4.8, we'll let S be the set of all polynomial linear combinations of a of x and b of x. So S will be the set a of x, mx plus b of x times nx, as m of x and n of x range over all elements in f bracket x. First, we want to apply the well-ordering axiom to show that S has a monic polynomial t of x of smallest degree. And second, we want to show that this polynomial t of x is the greatest common divisor of a of x and b of x. Now, we cannot apply the well-ordering axiom directly to the set S, however, since it is not a set of non-negative integers. The well-ordering axiom tells us that a non-empty subset of the set of non-negative integers has a smallest element. But our set S in this theorem is a set of polynomials. Instead, we need to apply the axiom to the set of degrees of polynomials in S. Now we need to first show that our set S is non-empty. And note that a of x times 1 plus b of x times 0 equals a of x. And a of x times 0 plus b of x times 1 will equal b of x. So this shows that a of x and b of x both have the form of elements in S, namely they are polynomial linear combinations of a of x and b of x. So both a of x and b of x belong to S. So this tells us that the set S is non-empty and has non-zero polynomials. Since a of x and b of x are not both 0, it follows that S contains at least some non-zero polynomials. So then the set of all degrees of polynomials in S is a non-empty set of non-negative integers. So this means we can apply the well-ordering axiom to the set of degrees of polynomials in S. So the well-ordering axiom implies that the set of degrees has a smallest element, which means there exists a polynomial w of x in S that has the smallest degree among all polynomials in S. So let's let r be the leading coefficient of this polynomial w of x. Then t of x equal r inverse times w of x will be a monic polynomial with smallest degree among all polynomials in S. Since t of x is in S, then there exists u of x, v of x, and f bracket x, such that t of x is the linear combination a of x, u of x, plus b of x, v of x. So we now want to show that t of x is the greatest common divisor of a of x and b of x. That is, t of x equals d of x. To show this, we need to show t of x satisfies the two conditions in the definition of the GCD. First, it's a common divisor of a of x and b of x. And second, for any other common divisor of a of x and b of x, the degree will be less than or equal to the degree of t of x. To prove 1, we'll use a proof by contradiction. So we want to prove t of x divides a of x. We'll suppose that t of x does not divide a of x. We then need to derive a contradiction. By the division algorithm, dividing t of x into a of x, there exist polynomials q of x and r of x in f bracket x such that a of x is equal to t of x times q of x plus r of x, and either the remainder r of x is 0 or the degree of r of x is less than the degree of t of x. Now, since we're supposing that t of x does not divide into a of x, the remainder is not 0, which means that the degree of r of x must be strictly less than the degree of t of x. Now, solving for r of x, we obtain r of x equals a of x minus t of x times q of x, and substituting t of x equal the linear combination a of x u of x plus b of x v of x, we obtain r of x is equal to a of x minus that linear combination times q of x. And then distributing q of x over the two terms, we get a of x minus a of x u of x q of x minus b of x v of x q of x. Now the first two terms on the right have a common factor of a of x, and we can factor a of x out of those. So we'll have a of x times 1 minus u of x q of x, and then minus b of x times the quantity v of x q of x, grouping the v of x q of x together. Now this shows that r of x is a linear combination of a of x and b of x. So r of x belongs to S. But the degree of r of x, we said, was less than the degree of t of x, and t of x was an element of S with the smallest degree among all polynomials in S. So this gives a contradiction. And the contradiction arose from supposing t of x did not divide a of x, so therefore t of x divides a of x. Now a similar argument shows t of x divides b of x. And so this proves 1, that t of x is a common divisor of a of x and b of x. To prove 2, we need to show for all c of x in f bracket x, c of x divides a of x and c of x divides b of x implies the degree of c of x is less than or equal to the degree of t of x. So we'll suppose c of x in f bracket x is an arbitrary polynomial. Suppose c of x is a common divisor of a of x and b of x. We need to show the degree of c of x is less than or equal to the degree of t of x. Now, since c of x divides a of x and c of x divides b of x, then there exists r of x and s of x such that a of x equals c of x r of x and b of x equals c of x s of x. So then t of x equals a of x u of x plus b of x v of x. And substituting a of x and b of x, we obtain this expression. And this has a common factor of c of x on the right side, which we can pull out. And this implies the degree of t of x is greater than or equal to the degree of c of x, as required. So this proves 2, and therefore t of x is the greatest common divisor of a of x and b of x, and hence t of x is equal to d of x. It remains only to show now that the greatest common divisor is unique. So suppose suppose s of x also satisfies the conditions for the GCD for a of x and b of x. We need to show s of x equals t of x. So since s of x is a common divisor of a of x and b of x, then there exist polynomials f of x and g of x such that a of x equals s of x f of x and b of x equals s of x g of x. Then t of x, once again, can be written as the linear combination a of x u of x plus b of x v of x, and substituting for a of x and b of x, we obtain this. And this has a common factor of s of x on the right side, which we can pull out. And it follows from Theorem 4.2 that the degree of t of x will be equal to the degree of s of x plus the degree of f of x u of x plus g of x v of x. Now, since t of x and s of x both satisfy the conditions of the GCD, then their degrees must be equal. It then follows that the degree of f of x u of x plus g of x v of x must be 0. And therefore, f of x u of x plus g of x v of x is a non-zero constant polynomial. So we can write it as c for some c in f, c not equal to 0. So then t of x will be equal to c times s of x. Since both t of x and s of x must be monic, however, then their leading coefficients are both 1. So this tells us that c is equal to 1, which implies that t of x equals s of x as required. And thus the greatest common divisor is unique. And this completes the proof of the theorem. Now the analog of corollary 1.3 is the following result. This is corollary 4.9, and this can be proved from the theorem. So let f be a field, let a of x be of x, and f bracket x not both 0. A monic polynomial d of x in f bracket x is the greatest common divisor of a of x and b of x if and only if d of x satisfies the two conditions. First, d of x is a common divisor of a of x and b of x, and second, if c of x is another common divisor of a of x and b of x, then c of x divides d of x. Now, two polynomials a of x and b of x in f bracket x are relatively prime provided their greatest common divisor is 1. The proof of theorem 1.4 can be adapted to prove the analog of that result, and this is theorem 4.10. So let f be a field, and let a of x, b of x, c of x be polynomials in f bracket x. And then if a of x divides the product b of x times c of x, and a of x and b of x are relatively prime, then a of x divides c of x. So if a of x divides a product of two polynomials and is relatively prime to one of them, then it must divide the other. Next, we want to look at the Euclidean algorithm. So the Euclidean algorithm carries over to f bracket x and can be used to determine the greatest common divisor of two polynomials. So the one modification is that since the last non-zero remainder when applying the algorithm may not be monic, it may need to be multiplied by a constant to obtain the GCD, since by definition the GCD is a monic polynomial. We start by dividing the polynomial with the smaller degree into the polynomial with the larger degree. If the two polynomials have the same degree, then divide either one into the other. Then the divisor in each line becomes the dividend in the next line, while the remainder in each line becomes the divisor in the next line. For an example, we can find the GCD of a of x equal x to the fourth plus x cubed minus 5x squared plus x minus 6, and b of x equal x cubed minus 2x squared plus 3x minus 6 in cube bracket x. So we start by dividing b of x into a of x. And we obtain a of x equals b of x times our quotient x plus 3 plus the remainder minus 2x squared minus 2x plus 12. So we do this by using long division, which I'm not showing here. Next, we divide the remainder minus 2x squared minus 2x plus 12 into the divisor b of x. And we obtain b of x is minus 2x squared minus 2x plus 12 times minus 1/2 x plus 3/2 plus a remainder 12x minus 24. And again, we do this using long division. Then divide the remainder 12x minus 24 into the divisor minus 2x squared minus 2x plus 12. And we obtain minus 2x squared minus 2x plus 12 is 12x minus 24 times minus 1/6x minus 12. That should actually be minus 1/6x minus 1/2 plus 0. Okay. So now we have a zero remainder, and the last non-zero remainder is 12x minus 24. And so multiplying this by 1/12, we obtain the monic polynomial x minus 2. So this is the GCD. Now, as with integers, we can use the calculations in the Euclidean algorithm to write the greatest common divisor as a linear combination of a of x and b of x. Start by solving for the remainder, which is the GCD, in the next to last equation. Then use the preceding equations to substitute for each remainder. So in our previous example, solving for our last non-zero remainder, we obtain 12x minus 24 is b of x minus 2x squared plus 2x plus 12 times minus 1/2 x plus 3/2, and then substitute for the remainder minus 2x squared plus 2x plus 12, and we obtain b of x minus the quantity a of x minus b of x times x plus 3 times minus 1/2 x plus 3/2. And multiplying out the terms on the right side and collecting the terms involving b of x, we obtain b of x times 1 plus x plus 3 times, that should be minus 1/2 x plus 3/2, and then minus a of x times minus 1/2 x plus 3/2. And then multiplying out the terms in the brackets and collecting like terms, we obtain b of x times minus 1/2 x squared plus 11/2 minus a of x times minus 1/2 x plus 3/2. And we can factor out a 1/2 from the terms on the right. And so this will be b of x times 1/2 times minus x squared plus 11, plus factor out a minus 1/2, and we obtain a of x times 1/2 times x minus 3. Finally, multiply by 1/12 to obtain the GCD, and we obtain x minus 2 is b of x times 1/24 times minus x squared plus 11 plus a of x times 1/24 times x minus 3. And so this gives us our GCD written as a linear combination of a of x and b of x.